Okay, let's unpack this. We're diving deep into a stack of material you've shared, all about getting a handle on how much space objects take up and, well, the area of their surfaces.
Right. Volume and surface area. Key concepts.
Exactly. Think volume and surface area. And we're focusing specifically on the fundamentals, using shapes like, boxes and cubes.
Basics, yeah.
Our mission in this deep dive is really to pull out the main nuggets from these sources.
The definitions, the formulas.
And crucially, how they actually apply, in the real world.
Absolutely. What's really fascinating about the material is how clearly it separates these two ideas.
Okay.
Volume, at its core, it's simply the amount of space a 3D object fills.
Like filling it with water, that kind of idea?
Precisely. That's its volume.
Right. And the sources make a point about the units being different, which is super important, I think.
Oh, definitely.
Volume is always measured in cubic units, like cubic meters or cubic centimeters. You'll see 3 titers 3 or ton 9 $2. And like 1 millimeter 33 is actually a million 3 meter 33. That's huge.
It is, yeah. Or the liquid conversion you mentioned, 1 liter is $1,000 centimeter 33. Useful stuff.
And then contrasting that, surface area is more about the skin of the object.
Exactly. If you could, unfold all the faces of a shape and lay them flat, the surface area is the total flat area they cover.
Measured in square units, familiar 2 or 2032?
That's it. So this naturally leads to, well, how do we actually calculate these for the basic shapes?
And your sources really zero in on 2 key ones, the cuboid.
Which is just a rectangular box, essentially.
Yeah, fancy name.
Yeah.
And the cube. So for any rectangular box, a cuboid, if you know its length L, its width or breadth B, and its height H.
Okay.
The sources show the volume is, well, quite intuitive. You just multiply those 3 dimensions.
U10 times B times H.
Yeah.
Stacking layers, kind of.
Exactly. The total surface area, that's a bit more involved because you've got 6 faces.
Right. Top, bottom, sides.
You calculate the area of each face length times width, width times height, length times height, and add them all up. Okay.
And since opposite faces are identical, the formula cleans up nicely to $2 times pound plus BH plus HLR.
Makes sense. And the cube is just the simplest version of that. A box where all edges are the same length, say A.
Precisely. If all edges are A, the volume becomes super simple. A times
But that's 823.
23, yeah. And the surface area, well, you've got 6 identical square faces.
Each one A22.
Right. Each with an area of A or 2 tellers. So
Yeah.
the total surface area is just $6 times A teller 2.
Okay, here's where it gets really interesting based on what you shared.
The applications.
Yeah, they don't just stop at the formulas. They show how these ideas solve, actual problems, like figuring out liquid capacity.
That's internal volume, yeah.
Or how much paint you'd need for a room. That's surface area.
And connecting that to the bigger picture, the example the sources give about calculating the material volume in a thick wall box is just brilliant.
So like a wooden chest or something.
Exactly. Imagine a wooden chest. The outside dimensions might be quite large, but the space inside the capacity, it's smaller because the wood itself takes up space.
Right, the thickness. So if you know the external length, width, height, and the wall thickness, the source explains you have to subtract twice the wall thickness from each external dimension to get the internal one.
Exactly. Twice. Because there's thickness on both sides of the length, both ends of the width, top and bottom for height.
Oh, okay. Got it.
So length minus double thickness for internal length, same for width, same for height.
Then you calculate the internal volume with those smaller numbers.
That's your capacity. And the actual volume of the wood, the material itself.
That's the difference between the big outer volume and the smaller inner volume.
Correct. It's a really clever application.
Yeah.
The sources also show, as you mentioned, calculating wall areas for painting, but importantly, subtracting the areas of windows and doors.
Very practical, applying surface area concepts directly.
Yeah, to things you encounter every day.
So, okay, wrapping this up, what's the big takeaway? We've gone from the basic definitions, volume versus surface area. Looked at the core formulas for cuboids and cubes straight from your sources.
Right.
And seen how they apply in real situations like these thick boxes or measuring rooms.
It really highlights how fundamental these geometric ideas are.
Yeah.
And this raises an important question for you, the listener, to think about. Drawing from the material.
Okay.
The sources touch upon combining shapes or maybe even melting down a solid object and recasting it into a totally different shape.
Ah, interesting.
Well, property, and think about it, volume or surface area fundamentally stays the same, stays constant during that whole melting and reforming process.